Here's the idea on problem 203, number 3. We're looking for a point in space such that the electric field due to charge particle Q1, I'll call that E1, plus the electric field due to charge particle Q2, I'll call that E2, which is going to be directed toward the negatively charged particle, is the two contributions, the two vector contributions add up to 0. Well, you can see that the only way these two vectors are going to add up to 0 is if they're along the same line, and the only way they're going to be along the same line is if we're at a point on the x-axis. So let's check out points on the x-axis. If we consider a point like this one, E1 would be away from 1, and E2 is going to be toward charge particle number 2. These two could conceivably add up to 0, except that E1 is actually always going to be greater in magnitude than E2 because it's got both things going for it. At the point in question, at a point like this, that's to the left of the origin, at a point like this, the point in question is closer to the positively charged particle, closer to Q1, so it would be bigger for that reason. And so E1 would be bigger for that reason. And also, Q1 is bigger than Q2, so E1 would be bigger for that reason. It's bigger for both reasons, so it's always going to be bigger if we're to the left of the origin. In between, E1 is going to be, as always, away from Q1, and E2, at that same point in space, is going to be toward, as always, toward the negatively charged particle. These two are both in the same direction, so there's no way the two of them are ever going to add up to 0 over there. If we consider a point over here, however, E1 is away from Q1 as always, and E2 is toward particle 2, and these two are in opposite directions, so they cancel. They could conceivably add up to 0. Furthermore, E1 tends to be bigger because Q1's bigger, but E2 tends to be bigger because we're closer to charge particle number 2. So we have competing effects. So this is the region where we can hope to find a solution. By the way, they're both 0 at x is equal to infinity and x is equal to minus infinity, so those two are solutions as well. But for non-zero value of our position variable x, we got to be to the right of charge particle number 2. Now, when we go to use the kq over r squared for both of them, r1 would be this distance, r1, which is just the x coordinate of our particle. Point P is at x, comma 0. So R1 is just going to be equal to x, how far over our point in question is, and from the origin, and this is R2. So R1 by definition is how far the empty point in space, let's call it point P, we'll give it a name. Point P is from charge particle number 1. R2 by definition how far point P is from charge particle Q2, and we have a relationship between them. By the way, I call it R1 is just equal to x, but R2 is, let's see, x, R2 is x minus d. In other words, d plus r2 gives you the x coordinate of point P, and subtracting d from both sides, I have r2 is equal to x. So you use this distance as r1, and this distance is r2 in the expression kq over r squared, and add the two of them up like vectors, E1 and E2. And solve for x. Set the sum equal to 0 and solve for x, and that's how you get the answer. And you got to find a value of x. It better turn out to be greater than 14 centimeters because we assumed that it was to the right of particle 2, meaning it's got to be greater than 14 centimeters.